Can I look it up?
Because of my maths. Yeah.
Right, hello ladies and gentlemen, we're two students from... Just kidding. I'll draw that up.
Both of you are well known to everybody here, I think.
I can do this as well.
Okay, so I'm gonna present you the following exercise we have to try to solve, and it's like known as the ladder paradox or ladder in the barn paradox. And I think it's easiest when I read through the to the problem, and then I will announce how we solve this. So we have like a 20-meter pole is carried so fast in the direction of its length that it appears to be only 10 meters long. So we have like a Lorentz contraction, and the runner carries the pole towards the front door of a barn which is 10 meters long. Just at the instant the head of the pole reaches the closed rear door, the front door can be closed, enclosing pole within the 10 meters barn for an instance. The rear door opens and the runner goes through. From the runner's point of view, however, the pole is 20 meters long and the barn is only 5 meters. Thus the pole can never enclose in the barn. So we have like a paradox. So actually what we have like two different frames. One of the barn where we are like looking at the barn and we see someone running into it with a ladder. And because he's like moving, we have like a Lorentz contraction. Maybe it's this is the barn. Okay, so this is the barn, and there's like one running with the ladder into the barn, and there's like a Lorentz contraction so that the ladder is 10 meters long. So one guy from outside will see that the ladder will fit inside the barn, and the other one sees that the barn is coming towards him. So the barn is shrinking, and he has like with respect to the ladder has like the ladder is 20 meters and the barn is shrinking to 5 meters. So there's like a contradiction, a paradox.
Who's that guy, by the way? Who's the second guy?
Let's imagine we have someone standing here, and someone carrying the ladder here.
That's a ladder.
So he is looking at the barn and at what happens from outside. So he's not moving into respect to the barn, and he is not moving to respect to the ladder. So we have like so let's divide it in two frames. So first the frame of the barn.
Under the barn and do the ladder?
Yeah, okay. Well, I think it's easier if you go step by step. Then there's like so we have to decide what are the events. So first event is like when the front of the ladder reach the front door of the barn, and we denote it as T0 for us out of simplicity. So T is 0 when the ladder enters the barn. And then we have when is the back of the ladder entering the barn. So by taking first of all, I forgot to say, so as we said before, the ladder shrinks to 10 meters. So we have like a contraction, and we can calculate the gamma, which is 2. Is it okay if I write it like this, or should I write?
Ask the audience.
Do you understand how we get the gamma from? So we have like L is like 1 over gamma LO. So if you take this algebraically, yeah, gamma is LO over L, and since LO is 20 and L is 10, we have 2. If we want to find out what the velocity is, we do also an algebraic manipulation, so that we get V is 1 minus 1 over 4 and that C squared, and what we get is 0.866 C. That's the velocity. It needs to have to shrink to 10 meters. Yeah. So if you take the velocity into account and the length of the ladder, which is 10 meters, the time the back of the ladder reach the front door is equal to T times
3.852.
Distance divided by velocity is like 3.852 times 10⁻⁸ seconds. Then we have also like the time. For example, the front ladder reached the back of the barn, which is the same time as this one because it's also 10 meters has to travel, so it's the same 3.852 times 10⁻⁸ seconds. And then we have the time where the back of the ladder reached this, for example, which will be then twice the time. So 2 times 3.852 times 10⁻⁸ seconds. Go to 7.70332. Okay. Did you want to do the?
Yeah, likewise, we do the same with the ladder frame. We again use the moment it enters as the beginning of our system of coordinates. It's a rod ladder object 0. Next moment is when it reaches again the back door. We could use some cause suppose that works. It's given by the long contracted length of the ladder divided by the speed. What was it? Yeah. No, I mean No.
It's 5.
What?
It's 5, no?
Oops. They're equivalent, the events, by the way, same order. Then this will be when the back enters when the entire ladder has entered the thing, which should be twice the time for this. And
Do you
time
understand
equals-
this? Yeah. So we took like this from the reference of the guy with the ladder. So this shrinks to 5 meters, and then we take the same events like when are they happening.
Wait.
Yeah.
For t prime, you say that 5 divided by 0.86 is equal to 1.92 times 10 to the
Yeah.
minus 8. How is that possible?
It's 0.866c.
Ah, okay.
Yeah.
Sorry.
And this is the time like the back of the ladder enters the front door, so 3.8 times seconds.
Question from me. I'm not sure what your frame, what the 3 times mean. I mean, I read them.
So basically we wrote down like different events, but
Yes.
not all the times like to say like from importance. So just first of all have a look what
Okay.
happens, but then we will put the Lorentz transformation into it, and then
I'm still struggling a little bit because the first one is the front of the ladder, which is the back of the barn. Can you point out what the front of the ladder is in your picture and the back of the barn?
the front ladder reach the back. So yeah, so this is the front and this is the back, and this is the front of the ladder and this is the back.
Oh, okay. So
Yeah.
okay. So the first one is when. Can I stand over there just to point out? So
I call them A and B, but it's front
Okay.
entrance, back entrance.
so that first moment in time is when this comes here.
No.
When this comes here.
This is 0.
And this is
Zero.
zero. Oh, that's
yeah,
it, yes,
0,
okay.
and then this is when the front reaches the
The
back.
back is B, that's the second.
Okay.
one
And
is-
then this, the third one is when the back of ladder, that's this one, the front, comes over there. That's his. Oh yeah, of course.
Which is just twice the
Yeah,
previous
yeah.
one.
I get it now. Yeah, of course that's the same number. Because your Lorentz factor of 2.
Yeah.
Yeah. Okay.
And what's the back of the?
Yeah.
So now we've defined all the events. Now we use the Lorentz transforms to see how the simultaneous events for one frame happen in the ladder frame.
So to be sure, we take the general Lorentz transform, like t prime is equal to gamma to t minus b over c squared x, to calculate what the time here, because in the frame of the barn, one door closed and the other one opens, so we want to see when the front door closes, what time it will be in the reference of the guy running with the ladder, what time it will be there, because like due to contractions and time dilation, it should be different. So we take the general formula to be sure that we make no mistakes, with the proper time, that we not confuse this. So by putting in gamma is equal to 2, then we take the time the front door closes in the barn reference is 3.852, when the back of the ladder is inside, the door closes. So we have 3.852 times 10 to the minus 8. And then we have the velocity divided by c squared, and x in that case is 0. So these terms fall away. And what we get is 7.702 times minus 10 to the 8 seconds. Okay. Then we want to see at what time does the door at the back of the barn opens in the guy with in the reference of the guy with the ladder. So we take again the same formula.
And 10 for x.
And then the only thing that changed is time is the same.
These two happen simultaneously but at different spatial points.
Yeah. V over c squared times 10x. And what we get is 1.925 times 10 to the power minus 8 seconds. So basically, what does this result tell us? If we look at the reference of the barn, the door and the front door and the back door, they close they open and close at the same time. There's like no differences. But if you go to the reference of the guy with the ladder, we have 2 different times. Here, that's the time. Can you go with that? This is the time the front door closes, and this is the time the back door opens. So they don't open and close at the same time. In this frame, simultaneity is not the case. Here there was simultaneity open and close, but here one thing happened before. The back door opens before the front door closes, so that the guy with the ladder, who sees the barn 5 meters long, so anyway too short to go in with the ladder and fit in, runs into it. The back door opens, he runs through, and after he has gone through, the front door closes, and there's like no problem in that sense that the paradox is kind of solved. And but then we were thinking of
Space-time interval.
yeah. So does that make sense for you? This? Yeah. Can you follow? Well, are there any questions? No. Okay. And then we were thinking of Well, imagine we would put a light sensor in the barn, so that the one door, the back door, can only open when the front door closes. So that in this case there would be a slight contradiction, because the back door cannot open before the front door closes. If you put like some mechanical things in between that implies causality, because here in the exercise there was not causality implied that one door should open only after the other closes. They were just saying this and this happened at the same time in that reference. And then we were trying to thinking of this, and we were trying to see if there can be causality between the two events at all. If the distance is not too important, so that information can pass to one to the other point. So we took the Minkowski integral, and I don't know, a lot of you saw it in the theory of relativity courses that the x dt, that's like the interval which, if it's positive, it's like a space like that. It says that there's like too much space in between, so that in that short time information could reach the other point. And that's like where we struggled and couldn't find any real answer, because in the reference of the barn, the two events happen at the same time. So this should give us 0, like delta t, there's no delta t, is 0. And x is 10, so like should us give 100, so positive. But if we plug in the results we got from the reference of the guy with the ladder, we have delta x prime, we have 5, and for c dt we have a certain amount in between the two events, and if we plug it in we get a negative number. So and we were like, that's not possible, since delta s has to be invariant for both references, and that's why we couldn't came to a conclusion, because
yeah, numbers are definitely correct as far as the x and t's go. So it makes sense that it's space-like, because one observes it simultaneously, while one of the two observes it simultaneously. So they should both be space-like, but only from one frame. This gives us a space-like result.
Okay, so you've done the calculation, just to recap, you've done the calculation in the barn frame, but you also did it for the ladder frame. How you did this was by first doing it in the barn frame, just no relativity, just T is D over V as such.
Yeah.
Then you used your Lorentz transforms to calculate what it would be in the ladder frame.
Yeah.
I'm not sure, you mentioned it, one of you, that the barn paradox was now solved. I'm not sure I followed that point, but ultimately what you get is your delta t's, your delta t primes, and your delta x and delta x primes, and they should give the same number for delta s or delta tau. And, and now you're saying that they don't.
Yeah.
Okay, so that's interesting, because the tricks that you've used, Lorentz transforms and such, follow from it having to be the same number. So there is something strange going on. That the rules that you've used that enforce that the Minkowski line element is the same number gives you numbers that are not the same.
I did some research, and the closest thing I could find was that maybe we didn't take into account that for the frame of the ladder, the barn is moving, the points are in movement, so you can just define the events as happening at x equals something. But I don't know how to use that for this exercise.
Well, it's open the floor. I mean, we all see that there's an issue here, yes? They got two sets of numbers, and substituted in the Minkowski line element should give back the same number. It doesn't. So that either means that there's an algebraic mistake, just typing in your calculator and something went wrong there, or there is some conceptual mistake. Maybe you used something that you were not allowed to use, or something like that.
I think I will go for the second.
Maybe we use the space-time integral. That's, we mean without the c squared. This is without the c squared, right? It's the same thing, but without the. Maybe we'll use that form. No, but I tried that already.
Everybody in the audience, feel free to contribute. There is an issue here. It's either algebraic or there is something conceptual. As it stands, there is a mistake somewhere.
For the
calculations you have on the right there for the barn point of view,
Yeah.
could you say T is D over V a few times, so you actually put in the numbers that you use, could you put in distances?
Sorry.
Calculate
So
that?
we put this number.
Yeah, I know the number you got out. If you like write down an intermediate step of going from D over V to the actual distance you use to calculate over the actual velocity using that.
So we take as velocity this velocity. So we took D 10 meters.
Okay, D is 10 there.
Yeah.
And the back of the ladder is adding the times for the front and the back together. This one and this one. It's pretty simple math. There's not a lot of room for error. But we have resolved the paradox.
Can you say something about that?
Because the paradox is how come one observer see the end and the back of the ladder reach the end on the back of the barn simultaneously, whereas for the other person it doesn't, and that happens because we demonstrate that simultaneity is not conserved.
Okay.
So, and we use Lorentz transform to demonstrate that.
So wait, I have a question. So that L0 you have there, that's no,
The rest frame.
that's your rest frame, right?
Rest length.
Yeah.
Rest length, sorry. But that L, how'd you get that? The other
It's
L?
like it's given in
It
the
actually
exercise.
is given.
It says that
That's
it
the
has 10.
smallest gamma you would need for it to
At
fit.
0 is 20, but when it runs, it shrinks to 10 meters.
Oh, just okay. Oh, then
It has to be
Yeah.
that.
So yeah, because I was confused about the fact that the two T's there are the same.
Yeah, because
But
the
that
barn is
makes
10
sense.
meters and the ladder is
Okay,
10
no,
meters,
yeah,
and then
yeah.
that gives that's why
Yeah.
the time there is the kind of the same. Yeah.
This is probably because I'm not in the right room. We'll see what happens.
Last time nothing happened.
We'll see how this unfolds.
Yes. See things unfold. Make ready for battle. Okay, but so just to have that point out of the way, the idea is that the barn paradox is solved because the paradox is, well, one person says the guy in the barn frame says, oh look, the guy is running just fast enough for the thing to fit, and then the guy who does the running says, excuse me, it's the barn that has now shrunk to a smaller size, so it really does not fit.
Yeah.
And then the question is, so how come either the thing fits or it doesn't? And your answer is, well, they don't agree on where the front end and the back end are at, because they have different opinions on that.
Yeah.
Right? I mean, if one guy says, well, that's the barn guy, he says, well, in order for you to make the measurement that it fits, you have to record where the front end is and the back end at the same time, because otherwise you get two numbers, but they won't constitute its length. And the guy who does the running says to the other guy, well, you're not taking your measurements of where my ladder is, the front and the back end at the same time, so therefore you don't end up with the right number. That's the resolvement of the paradox. Yes, okay. Still, the numbers game doesn't play out.
Do you know why it doesn't, or you also?
No, I'm really looking myself.
Great.
But we are sure that it should give us delta S of 100.
What are the two events that you're putting into your
But so we take the the two events we are looking as the opening and closing of the door.
It's
Yes.
simultaneous.
So
with the-
in one barn it's simultaneously, so there's like no difference in delta T.
That's in the barn frame.
Yeah.
Okay.
So this is 0, but there's always the spatial separation, which is 10 meters. So delta S should.
I think.
Yeah, what's delta S squared? So delta S squared should be 100.
Yes. Okay. So I think I agree with that statement. I mean,
Okay.
if the two events are,
Yeah.
I'm not going to say without the opening and closing of doors, but I think that your statement is the two events are for the barn guy,
Yeah.
the front end of the ladder. I'll just stand here so it's easy to point. Excuse me. That the two events are, this one is here, and this thing is there. Those are the two events. And I agree with you that for this guy, that's 10 meters apart. and because he took the measurement at the exact same time, the delta t is 0. So I think I agree with that statement. So that is correct.
But the other one looks correct too, because if you, so we have like these are the times when the one door opens and the one door closes and one door opens. So if you take the delta of this time, so that will give us 5 point something.
Yeah,
And it's different between these two events. So if you take
Yeah, you already have the number.
so
5.7.
it's like 5.7. So and we plug it in here. So what we have is, as I said, delta x, because the bond shrank. So the guy in ladder sees the bond 5 meters. So the events are separated by 5 meters. 5 meters minus c times the time, which is 5.735 times minus 8. We get a negative number, and that makes somewhat sense because
No, you cannot.
That means they can be. That means they can be causally linked.
Huh?
That means they can be causally linked, no?
What?
It's a negative number from the.
No, if it's negative number, that means that the distance, the light travels is greater than this, so that the information could have been passed to the other door. So that's the struggle. And that makes sense because if you look at the velocity there he's running at and the time he needs, the time between two events is enough so that information can pass and these two events can be correlated or by causality or so.
So isn't space like larger than 0? Space like is larger than 0.
Yeah, but this is time now.
There's one thing that I don't understand, and that is
That's right.
why did Panos write down in the middle of the board the amount of time that each of these 4 events, at what moment in time these 4 events happen, and at the left hand side he calculates the same numbers by Lorentz transform.
Additional information, it further demonstrates that these events cannot be simultaneous in both frames.
Yes, but you get different the t primes out. Your t primes in blue are different than your t primes in black. And which one did you use to check your Minkowski line element? Did you use the blue or black?
Yeah, in blue.
So when the front light reaches the back, 2. Well, these actually are the same. And yeah.
They look like different numbers to me. Did you use the black numbers to calculate the blue numbers?
No,
No.
that would make sense.
Okay.
But one is the same. The
Wait, which
ladder exiting.
And you took the 3.8.
The time for the ladder exiting is the same.
which delta t's are these? Which moments in time are they?
These two.
Yeah.
385. So that's the when the front ladder reaches the back of the barn, and what's the same number? What's the second calculation? What is the second calculation?
Because you changed the distance there.
Yeah, the distance. Yeah, so it's the same event, but same time, but at B, at point B.
Why is x 0 in your upper blue ones?
Well, it's like convention.
Because 0 and 10. They happen simultaneously, but at different axes.
So
But
question.
you should use dx, right? So you should always use the separation
Yes,
between
I
the
was about to
events.
say that.
Yeah, which is
You're
0 here.
just like absolute values of time, but not delta t's.
Doesn't the
delta
ladder
x's,
frame
so to
guy
say.
still see them? Two different
Yeah,
places.
that's
They're
what
not
I'm
Should we
actually-
include the time in the Lorentz transform? Is that it?
Because
No.
Lorentz transform only
Yeah.
applies to differences
Yeah, it's-
in
it's-
time, not
it's-
absolute
It's
distances in
duration
times.
and not.
Yes, exactly.
moments, Yeah.
Durations and distances. And
Yeah,
you've
durations
used them
and
for
separations.
moments in time and
Correct.
locations in space.
Yeah, yeah.
You should do with them.
And your location in time for that first moment, your location in space for this moment, when this thing enters here, that is indeed 0 because this is how you set up your experiment, right? That it enters at the moment at t0, that's written here. The moment that this part gets here, that's a separate event happens at a different location in space.
Yeah.
And the Lorentz transform applies to the difference in the locations of these two events, this event and this event. And that distance in space is not zero. The location is space for the first event, but the difference in these two events is not zero. It is, what is it? 10 meters.
So there are coordinates.
Yes, you've plugged in coordinates and not distances and durations. So this is where the mistake is.
But if we had that, be the same numbers as these.
Well, that should give the same number, yes.
Well, someone has a
So
calculator.
why was this one correct?
Yeah, we can easily just calculate it right
So
here,
this
right
one was
now,
correct
yes.
because we actually added the distance.
What is that?
It's the same as the ladder reaching me.
Then that value would be the same as the top one then. Because isn't the dx is 10. So the bottom one is kind of the correct calculation for the one above.
Back of the ladder reaches barn, that's 3.85. Who's using this calculation, gives you 1.92. Ladder reaches beam, same number. So at least this was correct.
Yeah.
Okay, because we added we thought we were adding coordinates, but we accidentally added the correct, we added an interval.
Yes, so the second one number should be the correct one,
Yeah,
yes.
Which is a number you already had. So
Yeah,
it's-
yeah.
Yes, okay, so at least the black and the blue now agree with each other.
Yeah.
That's good. Okay, so there's a big lesson here to be learned, and that is that it's a statement that I made last week. Relativity, either special or general, does not say anything about locations and moments in time. It says something about durations and distances. And it's a very easy thing to confuse. And you've used the Lorentz transforms now for locations and moments, and not durations and distances. But we've seen a mistake now, yes? So that's enormous progress. Can we still be sure about your resolution of the actual paradox? Because you hinged it on the non-simultaneity of two events happening. Does it still hold? Your resolution of the paradox?
Yeah.
Like conceptually, it still holds, right?
Yeah.
Well, if they had meant your delta t is here, delta t prime, the delta t and delta x, this number is still correct. This was not 0, it was some other number, but I'm pretty sure that if you subtract these two, if this, with the correct number for dx substituted, if this gives you 0, then there's no loss of simultaneity, right? Because it's going to be 0 time between the two events in the barn and in the ladder frame.
And what would the correct number be?
That is not simultaneous, because then the guy with the ladder can tell the other guy, you haven't measured my back end and front end at the same time. So therefore it looks as if the ladder does not fit. So what we have to check is whether this number is still some finite non-zero number. If so, you have still resolved the paradox. So what can somebody calculate what this is? 10 times v divided by c squared, and then something.
But the same.
So that's actually
Oh, that's this number. Okay, it's
Yes,
non-zero.
It is.
Okay.
Yeah, it's non-zero.
Okay, good. Because then the paradox is still resolved.
yeah.
Right? This is what the dt's should have been.
Yeah.
The paradox is still resolved. So again, there's this guy running with a ladder.
But not happening at the same time.
Sorry.
So these two t's would be the same.
But yeah, because they're literally the same
Yes,
calculation.
because they're exactly the same calculation.
Why?
So again, just as a resolution thing of the paradox, forget about the numbers for now. Just the fact that you get a non-zero number there for dt and you did get a 0 number there for dt means that the guy who did the measurement looking from the barn made sure that the front end of the back end of the ladder were measured at the same time. Then it concludes, look, it fits now because it has shrunk to 10 meters, the barn is 10 meters, so it will now fit. This guy, he sees the barn itself shorter, 5 meters now, still Lorentz factor of 2, so it will fit even less, right? That's the paradox, that one of the guys says my ladder fits and the other one says it does not. Now you cannot have a fitting and a non-fitting ladder, something is wrong here. What is wrong here is that the guy on the ladder is looking at the other guy in the barn, taking his measurements of the length of my ladder, and then he sees that guy not taking his front end measurement and back end measurement at the same time. So the guy running with the ladder says, excuse me, you're not measuring the length of my ladder at the same time. You're doing something wrong here. This is the reason why we're disagreeing. So that's the resolution of the paradox. And it hinges on the fact that that number is non-zero. Okay, so that's still there. And the only thing that might be still an issue is the Minkowski line element. But we've corrected our mistake now, haven't we?
Small question. If you would recalculate the Minkowski line element there,
Yes.
for the top one, where you have delta x is 10, would you... Oh, wait a second. I miscalculated something.
Okay. So I think the 100 is still correct. This is as seen from the barn. The two events are the front end of the ladder enters the barn, and the front end of the ladder enters the other side of the barn. Those are the two events. Right?
Why is the delta t 0 then?
Because, again,
This
Oh, yeah.
This is
Never
the
mind, I
right
see,
place.
yeah.
it's specified to be events are. This is event 1, that this part
I see.
enters this. The second event is this thing hits this thing, which is the same, by the way, as saying that this thing hits that thing. There's two events. And this guy, the barn guy, does the measurement, these two events, at the same time. So that means by definition it's dt is 0, and there's a 10 meter difference in between these two events. So this is correct, I think. And we now have to calculate this from the other guy's the ladder guy's perspective as well. What's the length of the barn as seen from this other guy's perspective?
10.
Divided by gamma, 5.
That's 5.
Yeah.
Okay. What's the difference in time between these two?
The value there. Where's it? Wait.
We still have an issue, don't we? Because how can you have delta x has gone from 10 to 5, so it gives you 25. You have to subtract something from that and hopefully end up with 100.
Negative time.
Imaginary. No, we still have not fully resolved it. Because even with the new numbers, your delta s squared will not give you 100. Even with the new numbers.
That's still negative.
That's a negative number.
But is the... Wait, so it's 10 from the guy holding the ladder? But isn't it...
No, it's 10 from the guy not holding the ladder.
Yeah, okay.
It's the barn guy.
Yeah.
You know, when we first wrote this, we used coordinates instead of intervals, right?
Wait,
But the numbers would be the same.
will it not make more sense if we take, like, because we take, yeah, it's 10, like, that's, like, the only way I see could be make sense, like, this has to be, like, greater than 10, otherwise we cannot
Yes,
have.
because
Maybe it's like 20, it's like the length of the ladder,
Yeah,
which
that's
is
what I'm
20.
thinking
Oh.
as well.
Maybe because it's not moving anymore, no.
So if we take the distances,
Yeah, like you look at the rest length.
So what would be the rest length then?
oh,
No,
because
no. Oh, no, you're right. You're right. Both of you are right.
We disagree with each other.
I think so. The guy on the ladder, he's looking where the front of the ladder is and where the back of the ladder is at two
Mm.
moments in time. What's the difference between those two locations? Is it 5 meters or what?
20.
That's 20. In his frame, it's 20.
Mm-hmm.
Delta x is 20.
In the frame of the ladder. Of
Yes,
the
because what he's doing, he's looking where the front end of the ladder is and the back end of the ladder is at the two events. But to him, there's always 20 meters difference between the two.
Mm-hmm.
That's
Okay.
the right one.
And it adds up.
Mm-hmm. Yes. But the time we use there is at 1.95 now, or the time we have there right now?
It's 3 times 5.7 because it cancels out. Oh no, it's
It should be
It's
one
weird.
at the bottom there, no? Okay.
Let's
So
do
you
it.
calculate, yes.
I mean,
Yeah, we're doing it.
we can reason that it's gonna.
Well, let's see.
It's still sub-zero.
This is no squared. It should be c times this
Okay,
squared.
yeah.
Okay.
So that's 3
It's
times
20 squared, right?
5.7,
20 squared
which
minus.
is
where- where's
16ish or
minus?
something like that.
Minus
Oh, that's 3. Yeah.
Square 100 squared.
Sorry?
No, we're trying to do this.
What is this? Has to be squared?
That's not the right
3
one.
times 5.7, it's
Is it
15,
not
plus
the
20 is 17 or
5.7?
something like that.
Oh.
Have to square that, 17 squared?
17 squared.
Yeah, something like that. I'm just mentally doing this calculation.
What? 17.
No, what I'm doing is this. C is 3.0 times 10 to the power plus 8. The 10 to the
Yeah.
power plus 8 cancels the minus 8, so I only end up with 3 times 5.7, which is
Okay.
15 plus 2.7, 2.1 or something like that. It's about 17. And then I have to square that whole thing. What is 17 squared? How much?
289.
289. I'm pretty sure that if you take the full number, you will get exactly 300.
Which makes 100.
Which makes 200 minus the 300 gives you exactly the 100 that we're looking for. Can somebody check?
I think
Yeah.
Is that because of
Oh, no, wait. Oh, wait.
the abbreviated version of that number?
Yeah.
Okay, I think so.
Yeah,
Okay,
that's,
okay, good.
then it's okay.
Then we should be fine, right?
Good.
Okay, so key message here?
Yeah.
Okay, correct. Great.
Yeah, and that's
Okay.
that's the thing because like we addressed a new problem with the light sensor, you remember? And then that's why we actually came up with this to see if they can be related. And this is like space-like, so they cannot be related like the two events. And that's what we expected. Otherwise, we had like a new paradox coming up if we put like with the light sensors.
Yes.
So this says that
Rather than the principle of relativity.
there cannot be a causality between one door closing and one door opening, and
Okay, I think we solved it now. Haven't we? Great, great.
Big emphasis on we.
Okay, so, no, it was a group effort now. I mean, we're all pitched in. So thank you for setting up the problem. Thank you for doing the calculations. And moral of the story, I think, is make sure that you understand that the Lorentz transforms or all of relativity is about distances and durations and not locations and moments. Okay, great. Thank you.